Hey everybody, Dr. A here, and in this video we're going to be exploring a second flexural stress example. So let's look at the given information. Here we're being told that if the allowable flexural stress the beam is made of is 1800 psi, compute the required section modulus. Okay, so let's take a look at this beam we're given. Here we have what's called a compound beam. Okay, so in this compound beam we have a fixed connection at point A. We have an internal hinge at point B, and we have a roller support at point C. The span from point A to point B is 10 feet, and then from B to C is 5 feet, and the entire beam is supporting a uniformly distributed load of 0.2 kLF. So let's go ahead and get started. So to get started, we're going to write solution, and we're going to set up our defining relationship, and that is that our maximum bending stress, sigma B max, must be less than or equal to an allowable bending stress. Okay, now the allowable bending stress or the allowable flexural stress is given to us. That's 1800 psi, so we know what this is. The question really is, how do we deal with this sigma B max? Well, if you remember, there were two ways of calculating sigma B max, okay? One way is we can use M max times a y bar value divided by a moment of inertia about a neutral axis, okay? Now, that's one way of solving it, my over I. Now, in this particular problem, we're actually being asked to compute the required section modulus. So we need to recall that section modulus is simply a moment of inertia value divided by a centroidal location value, okay? So because of that, we can also write sigma B max is equal to M max over S, okay, over section modulus. So now we have this flexural stress formula in terms of section modulus instead of moment of inertia and y bar, okay? So now what we can do is set this version of the equation up inside of this inequality. So we can say M max over section modulus must be less than or equal to sigma allow. Now, if we rearrange this, we can get the section modulus S must be bigger than or equal to M max over sigma allow. All right. Now, again, we were given sigma allow, so I can check that off. So at this point, what do we have to do? Well, all we have to do is solve for M max. So I'm going to put a note here. All we need to do is solve for M max. Now, in this particular problem, the easiest way to solve for M max is to draw the moment diagram of this system. So, and of course, to do that first, we need to solve for external reactions and draw the shear diagram. So really, when you look at this problem, it is a mechanics of materials problem, but the vast majority of what we're going to do in this problem is really just statics, okay? So let's go ahead and get rolling on solving for M max. This is a compound beam, so I'm going to say disassemble the compound beam at the internal hinge B, okay? And so I'm going to draw a free body diagram of both parts of this system. We have our internal hinge here. I've disassembled it. Let me draw this a little bit better. And we have, at the fixed connection, we have an AY. We have an AX that shows up, and we have a moment reaction that shows up. And then over here, we're going to have, a BY. We're going to have a CY. And we can draw a BX going in both directions here, and a BY on this side of things. So if you remember from statics, A compound beam or any compound system is just a system that has an internal hinge here. And the way we analyze systems like that is we disassemble the system at that internal hinge, and we look at a free body diagram of each part, okay? So let's go ahead and draw the applied loads here. So this was 0.2 KLF, and that was spread out over the entire system. So this is also 0.2 KLF, okay? So how do we analyze this? Well, you may be looking at this, you may be saying to yourself, wow, there's a whole lot of unknowns, right? If I go left to right, I've got 3 unknowns at A, I've got 2 unknowns at B, I've got BY and BX, and I have an unknown at C. So where do I begin? Well, we're gonna start the analysis with segment BC, okay? We're gonna say analyze BC first, since it only has 3 unknowns. So you always want to start with the segment that has the least amount of unknowns for you to solve for and apply your equilibrium equations to. So if I just start with my free body diagram of BC, so I'm only going to look at BC. I'm going to forget about AB for now. Just look at BC. You can just look at BC, and hopefully from your knowledge of statics, you can come to the conclusion that BY and CY are equal, and they're both equal to 0.5 kips reacting upwards, and BX is just equal to 0. Now, if you want some more details on how to solve for reactions and forces and moments on compound beams, take a look at my statics playlist. I have a video just dedicated to that concept. So for the purposes of this video, I'm going to keep moving now. So now I've solved for BY, CY, and BX, okay? Now I move on to a free body diagram of AB, all right? So I'm going to say free body diagram of AB. Now the thing we got to remember is that we calculated BY is 0.5 kips moving upwards, pointing upwards in free body diagram BC, which means that in free body diagram AB, BY is pointing downwards, but with the same magnitude. So this BY has the same magnitude as the BY we just calculated, but it is pointing down, all right? So looking at free body diagram AB, I'm going to say sum of the forces in the y direction equals 0. And I can show a little work here and say AY minus 0.2 KLF times 10 feet minus 0.5 kips equals 0. And I can get AY is 2.5 kips reacting upwards, okay? Now looking at free body diagram AB, I can say sum of the moments about A equals 0, and I can say MA minus 0.2 KLF times 10 feet times 5 feet minus 0.5 kips times 10 feet equals 0. And so I can get my reaction moment at A is equaling 15 kip feet reacting counterclockwise, okay? And then, of course, by observation, when you sum forces in the x direction equals 0, we get AX is 0. All right, and again, see my other video in my statics playlist where I go into a deeper discussion and show more work on how to calculate these values. So now that I have all of these forces and this reaction moment, now I can draw my shear diagram, all right? So let's go and do that next. I'm going to draw my shear axis V in kips. There we go. So moving left to right, I'm going to jump up by 2.5 kips in my shear diagram. And then I have that uniformly distributed load. Now that uniformly distributed load is over the entire length of the beam, okay? So when I reassemble this point B, I'm just gonna apply that uniformly distributed load over the whole beam, all right? And so when I do that, I'm gonna end up getting a shear diagram that starts at positive 2.5 and it goes all the way down to negative 0.5, and it's going to be linear. Let me draw that a little bit better for us. It's going to be linear, and then CY is going to close me off at 0, okay? Now this point right here is going to be equal to 2.5 feet, okay? That's 2.5 feet there, all right? So that's my shear diagram. Next, I'm going to draw my moment diagram. Here's X in feet, M is in kip feet. And I'm going to use the graphical method, just like we learned in a statics course. So we jump down to negative 15 kip feet, and we're going to find the area underneath these the shear diagram segments. And so my moment diagram is going to look a lot like this. Draw that a little bit better for us. Oh, that's not very good either. There we go. Okay, now this point right here from the shear diagram is going to correspond with that maximum point on the moment diagram, and technically this point right here is 10 feet. This is not drawn to scale, so let me put a note here. This high point, by the way, is 0.625 kip feet. These are not to scale, okay? If you draw these more to scale, they'll be a little bit more stretched out horizontally, all right? Regardless, the maximum moment we're gonna get here is this negative 15. So we're gonna say use M max is 15 kip feet. So because the problem itself did not specify that we were looking at a maximum positive or negative moment, just take the absolute maximum. The absolute maximum is 15 kip feet. So finally, we can solve for that section modulus, and we could say the required section modulus is equal to M max over sigma allow. And we got to watch out with our units. We're going to say 15 kip feet times 12 inches per foot divided by 1.8 KSI. That was the 1800 PSI that we were given in the problem statement. And this comes out to be about 100 inches cubed. And that is our final answer. So the required section modulus must be bigger than or equal to 100 cubic inches. So this is kind of like an introductory type of design problem. If you were designing this section, this is kind of the process you would go through to calculate the cross-section property. And then what you could do is you can select a cross-section geometry with a section modulus that's bigger than or equal to 100 cubic inches. And again, I kind of went through the statics calculations fairly quickly because I'm assuming we all are fairly comfortable with statics. So if you are a little rusty on handling compound beams, do some review on your own. Maybe take a look at one of my statics videos to help you navigate that. So that concludes this video. Thanks for watching. If you found this helpful, please hit like and subscribe.